Hello everyone, welcome back. If you are new, this is a new series that we have started in which we are trying to dissect segment trees from scratch. In the previous four videos in the series, we have already discussed what is the basics of segment trees, how to do point updates, range queries, how to perform the complexity analysis of each of these, and we have also gone through a code walkthrough. After that, we jumped onto a specific class of problem wherein you are asked to query on the prefix of an array. We looked at several different problems, and after that we solved two follow-up problems as well, which are of decent difficulty. Like code forces E and D are not uh, actually very easy problem. They are decent difficulty problems, and we have solved both of them in the previous two videos. And as discussed, we are going through this list of problems. We already discussed these two, and in this video we are going through this one. So if you haven't watched any of the previous video, I would encourage you to watch those videos as well so that you can follow along completely. But not all the videos are a prerequisite of this video, and you can still watch this video if you haven't watched the previous videos. So with that, let's get started. So the current problem is longest increasing subsequence. So the problem is you are given an array and you need to return what is the length of longest increasing subsequence in this given array. What is a subsequence? Subsequence is just a sequence of integers from this array without changing its order. So a subsequence can have 10, 3, 6, 4, right? But a subsequence cannot be 10, 1, 3, 6 because you can see 1 and 3 have changed their order. So basically the constraint in subsequence is the order should not be changed in the resulting array that we are forming. So you have to form the longest increasing subsequence. For example, in this case, the longest increasing, there are various longest increasing subsequence. One of them is 1 to 9. You can see you can form 1 to 9 without changing the order, and this is strictly increasing. And the length of this subsequence is 3, and hence the answer for this array would be 3, right? So if you are seeing this problem for the first time, I would encourage you to pause the video and try to think of a brute force solution for this problem first. If you already know about that, you can continue. So what we need to find the longest increasing subsequence. Let's say the longest increasing subsequence ends at this particular index, right? Now what is the previous element for that subsequence? So what we're saying is there is a subsequence which ends at 9. Now what is the previous element of this subsequence? The previous element of this subsequence should be smaller than 9, first of all, and secondly the index of that element would be smaller than the index where 9 was present, right? So j should be less than I, right? So in this particular scenario, j could be anything in this range, right? Now let's say you figure out that this is j because this satisfies both the condition that the element is actually smaller and j is less than I. So 2 is less than 9 and also the index of 2 is less than index of 9. Now let's say this is j. Now what you need to find, you can say, okay, find me the length of longest increasing subsequence that ends at 2, right? Because you wanted to find the longest increasing subsequence that ends at 9. You said that, okay, I now have taken 9 already. Now I know that the previous element of the subsequence that I'm forming is 2. So what I can simply say, okay, find me the longest increasing subsequence that ends at 2, right? Whatever the length I will get, I will just add +1 and that would be the longest increasing subsequence that ends at 9, right? So if you think about it, this is exact same problem which we were trying to solve, just that the length of the array is now reduced, right? So previously we were asked to find out the longest increasing subsequence that ends at I. But now we are saying that, okay, find me the longest increasing subsequence that ends at some j and where j is less than I. So basically we have reduced the array and we are solving exact same problem. So hope you can see the recursion here. the formal recursive function would look something like this. So we have to find the longest increasing subsequence that ends at a particular index I, right? Now we will, for this index I, we will try all possible index j which is less than I. So basically we are trying to find out what is the previous element of I. So previous element of I can be anything which is less, like the index of whose is less than I, and the value also is less than the value of current element I. So we are checking, we are iterating over every element which are less than I, and for all those element which are, whose value is actually less than the value of array I, we are calling the same function again. So this function would give us what is the length of longest increasing subsequence that ends at j. Now after j we will have I, ith index, right? So longest increasing subsequence that will end at I would then be 1 plus this particular length. We will just take the maximum over all such possible j, and whatever gives us the maximum, that would be the value of longest increasing subsequence that ends at I, right? Now with this function we will know what is the longest increasing subsequence that ends at 9, let's say. What is the longest increasing subsequence that ends at 2, similarly, so for others as well. And finally we will take the maximum over all of those. So let's say the longest increasing subsequence that ends at 9 is 3, longest increasing subsequence that ends at 10 is 1, that ends at 8 is 1, and so on and so forth. So we will just take the maximum over all these numbers, because we just need to find the longest increasing subsequence. We don't need to say that whether where this subsequence will end. So this subsequence, the final subsequence can end here or here or here or anywhere in this index. So after finding out the longest increasing subsequence that ends at a particular index I, we will just take the maximum over all possible I, and that would give us our final answer, right? So hope this entire solution makes sense. What is the time complexity of this entire solution? Uh, we are, how many unique times you can call this function, the value, number of unique values of I. So how many number of unique values of I can be there? N, right? And inside this function you are actually doing a loop, and inside this loop we are doing some constant operation. So each of these invocation would take order n time as well, because we are iterating over a loop. So final complexity of this algorithm would be order n square if you do memoization. Basically you are making sure that you are not computing one index more than once, and final complexity would be order n square, right? Now if you have seen this problem for the first time, I would strongly encourage you to pause the video right away and try to get this submitted in the lead code interface itself. So it actually gives you the exact same problem. You can just try to submit this problem, this solution there, just to make sure your understanding is correct. So we now know that we have a solution to find the longest increasing subsequence. Uh, what is the solution again? Just to reiterate, we will calculate the array where each index would denote what is the longest increasing subsequence that ends at that particular index. So this value will denote what is the longest increasing subsequence that ends at 2, longest increasing subsequence that ends at 4, and finally we will take the maximum over all the elements in this array, and that would be our answer. So basically our goal is to create this array as fast as possible. Currently, we are able to create this array in order n square time. We need to reduce this to order n log n. That is our motive. So, how to do that? So, for that, let's first try to convert this recursive function into an iterative function, because that would give us much more insight. So, whenever you have to reduce the complexity of the recursive function, the first thing that you should try is just try to code that in an iterative way, because when you do iteration you will see some, like you will have much more clarity over what kind of operations are getting performed, and you can do some pre-computation to fast them as well. So in this case as well, let's try to convert this to an iterative version. So the iterative version would look something like this. What we are doing, we initialize result of 0 as 1 because we know the longest increasing subsequence that ends at index 0 would be 1 because there is only one element in the first place, so longest increasing subsequence cannot be more than length 1. After that, we are applying this exact same trick, but the difference here is we were calling this function before because we are not sure whether the value of j was calculated or not. But in the recursive function we are actually iterating from left to right. So if we are at a particular index I, we already can be very sure that all the values for index which are less than I is already calculated. So we already have the values for every index I minus 1, I minus 2, everything right there. So for every j, we already have the value stored in our result array. So we initialize result 0 at 1 and then we are trying to calculate the values for result array one by one from 1 to n. What we are doing, exact same thing that we are doing here. We will just iterate over all the j's which are smaller than I, and we will check if the element value is actually smaller or not. If it is not smaller, we'll continue. Otherwise, we will consider that as one of the previous element of I. So understand, like we are again trying to calculate what is the length of the longest increasing subsequence that ends at I. So I is already there. We are trying to find out what is the previous element of I again. So for that, we have to make sure that j is less than I and the value at j is also less than value at I. So that's what we are doing. We are applying the same loop here and just taking the maximum over all the results array, right? So this is what the pseudocode would be for the recursive counter, like for the recursive counterpart of this, right? So let's now forget about this, and this is our new function which we will work at. So notice what this thing is doing. We are actually iterating over all the j's which are in the prefix of I and which are smaller than I. And then for all such indexes, we are taking maximum, right? So in other words, what we are doing here is find me the maximum over the prefix of I, which is whose value is smaller than array of I, right? Now this problem is very similar to the last problem that we have discussed, which is 459D. Here as well, we have to find exact same thing. We have two arrays. The first array we are considering that to update our uh, structure, and second array we were considering to do queries. So if you haven't watched this particular video, I would link that somewhere in the description down below or somewhere in the top right eye section. You can watch that. Basically now this problem is very much similar to that problem that we have solved before. So if you have watched that particular video, I would strongly encourage you to pause the video right away and at least give 30 minutes to think about how to model this problem into that problem and solve it in order and login. If you just watch the video, you will not be able to understand the core concept by yourself. So again, strongly encourage you to pause the video and try this problem at least for 30 minutes before jumping into the next section of the video. So what uh, we want to iterate over all the elements which are in the left of I and which are smaller than array I. And from all such elements, we have to figure out the maximum, right? So as we have done in the previous one, we will simply maintain two different things. So we have to build this result array at the end, right? And we have to only iterate over all the elements which are smaller than array I and which also lies in the left. So if you remember what we have done previously to find out the number of smaller element in the left, we just sorted the array so that each element here maps with something. So 10 maps to this position, 8 maps to this position, and so on and so forth. Now, if we need to just find out, let's say, the element which are smaller than 6. So we know already that 6 maps to this position. So everything in the left would be smaller than 6 because this array is something that we have kept sorted. So we know everything in the left of 6 is already less than 6. But there are two constraints. One, they should be smaller, which we have taken care of. And second, the index should also be smaller. So you can see 4 and 2 are in the right of 6, but here 4 and 2 are in the left of 6. So we need to somehow take care of these scenarios as well, wherein we will only consider the elements which are in the left of a particular element 6. So for that, if you remember what we have done, we simply mark the elements which are in the left. So 1 and 3 are in the left, so we'll just mark 1 and 3 and we'll consider only 1 and 3, right? So in this particular scenario, we have to take maximum over result. Like previously we were marking because we have to count the number of elements, but here we have to take maximum over a particular number. So previously we have to do range sum to count, right? And now we have to take the maximum, so we will just do a range maximum over this range. Now, because we are doing range maximum, we will just neutralize this with 0 because we know that max of 0 and x would become x itself, right? So we will initialize everything with 0, and only the elements which are in the left would be non-zeros. So in this case 3 would be some x and 1 would be some y. Now we can simply do range maximum over this range, and we will get the output of this result, this loop itself, with just doing a range maximum query over this range, right? So let's just iterate over this one example to get better understanding. So this is our array for which we need to find out the longest increasing subsequence. We sorted the array so that each element here maps to one particular index here. So that's how we sorted the array. Now we have to build this result array. So initially result of 0 would be 1 because we know that the first element here, you can't, like, the maximum increasing subsequence that you can form with just one element is 1. And as discussed, we will update this 1 into this position because 10 maps to this position, right? So we will update 1 here, right? Everything else is 0 currently, right? Now let's talk about this particular index. We are at this particular index. Now we have to again find number of longest increasing subsequence that ends at this particular index. So we will do a range query. Basically, we have to get the output of this loop, right? So we'll do a range query over everything which is less than 8. Now everything which is less than 8 is this range, right? Now in this range we will do range query, but we have to only consider the elements which are in the left. Now, because we have only marked the elements which are in the left, so we can simply do a range query and we can be assured that we will only consider the elements which are in the left, because all the elements in the right are something which we haven't touched yet and they are already 0, and maximum of 0 comma x would always be x. So hence here uh, we have to just do a range max query, and range max query of this would result in 0, and hence the maximum or the output of this loop would be 0 plus 1, which is 1, like y plus 1, because we were also adding 1 here. So we just get the maximum over result j, but after that we also have to add 1 as well, right? So that's where the result of this index would be 1, and we will update 1 here as well because this 8 will map to this particular index, right? Now let's go to the next index. For 3, again we'll do the same thing. We will find out the element or the position of 3, and once we find out that, we have to do a range query over all the elements which are less than 3. Again, doing the range query would give us 0, so the value here would be 1, right? And we will update 3 to 1 as well. Let's move forward. For 1, uh, same thing, we will look at 1 here, so 1 would be found at here. We will do a range query over this range, basically nothing, which is 0 again. So the value here would again be 1, and we'll update this to 1 as well, right? Now, now comes this particular index 6. Again, we go to the 6 position, and everything in the left would be smaller than 6. So we'll just do a range query over this range. Range max over this range would give us 1, right? So the value here would be 2, would basically 1 plus 1. Now you can, what does it mean? It means that there is a length of longest increasing subsequence that ends at 6 is of length 2. And you can see 3 and 6 is one possible subsequence. So it ends at 6 and it is of length 2. Similarly, 1 and 6 is one possible subsequence. It also ends at 6 and it has also a length of 2, right? So this like basically the 2 value here makes sense. Now again, we'll update this to 2, right? Now comes 4. Finally, you will do range query in this range again. Again, you will get 1 and you will update this to 2, and this will again be 2. Now comes 2. For 2, you will do a range query in this range. You will get 1 and this would be updated to 2, and this would be 2. And finally for 9, what you will get, you will do a range query over this range, right? And the maximum over this range you will find as 2. You will do plus 1 and this value would become 3, and you will update this to 3. Now finally you will take the maximum over all of these. It comes out as 3, and 3 is the answer. Basically the length of longest increasing subsequence of this array is 3, right? So hope this entire solution makes sense. Let's quickly look at the pseudo code. uh, the pseudocode is exactly similar to the one that was there for the previous uh, code for this problem. So what we are doing, we are maintaining this mappings first. Basically, which index of this sorted array does the index I would map to. So for that, we have created a positions map where each value here would denote what is the position of that particular index in this array. So basically map position of 0 would be 7 here, because 0 would map to 7. Similarly, position of 1 would be 5 here, and so on and so forth, right? So how to build position array? Very simple. We'll just sort the values and apply it to our map. Now notice that there can be duplicates in the array, as we have discussed in the previous video. Now because there can be duplicates, we can just maintain indexes as well while sorting the array, and just use that index to maintain the position, right? Now once you figure out the map, the rest is simple. We will just update the first index to 1, and then we will iterate from 1 to n. And for each index I, what we have to do, we have to first figure out what is the position in which you have to query. So for 10, you have to query in this range, right? So you have to figure out this particular index I. So this particular index I would be the lower bound of 10 in this array, like in this sorted array, right? So now notice that I haven't actually looked at the position array, because if you can say that okay, 0 can map to this particular index, so why actually we are doing lower bound? Why not just look at the position array and get that okay, 7 is the index that I want? The reason being, let's say if there are more than one like there are repetitions, let's say there are more than one tens, so this can be 10, this can be 10. Now it may happen that one of the tens here map to this particular index, right? But what you need to query on, you need to query on all the indexes which are smaller than 10. So basically you have to query starting from 0 up till here, right? Yeah, you still have to query in this range. You don't want to query in all this range, right? So that's where we have to do lower bound here, so that we get to the first index which has this value. Now once we get to the lower bound, we can simply query on 0 to index minus 1 and do a plus 1 here to get what is the value of the current index. Once we get the value of current index, we can simply update that particular position in our tree, right? So after this loop ends, we will have our result array built out. We can simply do a uh, either a range maximum over 0 to n, right? Or you can also do a range maximum by just querying the indexes one by one. Anything is fine, and that will give you the final answer, right? The time complexity is order n log n. We are doing sorting, so this will take order n log n. And again, inside this also we are doing two operation. We are doing a lower bound that would take order log n. We are doing a query that would also take order log n. We are doing a point update that will also take order log n. So the final complexity here is order n log n, right? So again, if you have watched till this point, I strongly encourage you to pause the video and try to code this solution yourself. Also, don't try to copy the segment tree code from the previous videos or any of the templates that you might have. Always try to code the segment tree class as well by yourself whenever you are practicing. That would help you understand the segment tree and retain that in memory for a long time, right? So strongly encourage you to pause the video and try to code the entire solution including segment tree class by yourself. So next we'll look at the code. The code is exactly similar to what we have discussed. We have first built the positions map. We have sorted, like we have kept value and indexes, value array of pairs where first element is the actual number and second element is the index. Now why we have to do this? Because numbers can repeat, and because numbers can repeat, we simply can't rely on one position array. To get this concept much better, I would encourage you to watch this particular fourth video wherein I was trying to explain why we need to do this array comma index mapping and why not a simple map would work. So I would link that somewhere in the description down below. You can watch that. After we have figured out this position map, we will iterate over all the indexes one by one. We'll find its position. So again, this can be moved as well. So basically, this is only required here. So you can keep it like this. We first find out the lower bound, basically the first index in which we have to query in. So if it is 10, we will look at the first 10 in this list. So once we get the first in this list, we will simply query from 0 to L minus 1 or index minus 1. Now notice that the segment tree function that we have written will give us the value in a range x comma y. Now if x is greater than y, this query solution will not work. So that's why we have checked if LB is greater than 0, then only we will call segment tree. Otherwise we know there is no index at all and we will just return 0 directly. Now once we get the value of current index, we will update the current index in the segment tree. Now segment tree function is exactly similar. What we are doing, we have these two public methods which will take in index and value and will call the internal private update method. Similarly, this query method which will take in to arrange x comma y and will call internal query method. And as discussed before, we are representing the segment tree in an array format, and to represent that we need three things: L, R, and I. L and R is actually the range which the current node denotes, and I is the index in the array. So basically L and R would be something like this. So this is L and I would be the index. So we are representing this entire segment tree in an array. So I would be the index of this particular uh, index in this particular segment tree array, right? After this, we mm, do the basic segment tree stuff. Like we just look at if we have to go left or right, and once we reach the leaf we'll just update that particular value. And this because we have updated one either of left or right, we have to recompute the value at the root. And what is the function that we are trying to store? We are trying to store the maximum, so we'll just do maximum of left and right. Now query method is again very similar. If the current node doesn't match at all, we will return 0. Now why 0? Because 0 is the neutralizer here. Basically we have to return something from here which would not interfere with the final answer. So if we would have asked for finding the minimum in the segment tree, we would return infinity, because minimum of infinity comma x would be x, right? Similarly, we have to return here maximum. So we have returned 0. We can also return minus infinity, but we as we are sure that every element in this array would be positive, so 0 would also do, right? So after that, we check if the current node completely overlaps with the range x comma y. If it overlaps, we'll return that particular value. Otherwise, we just return the max of left and right? So hope this entire solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I would happy to answer. Now, going forward, uh, I will skip this problem 4 dosa. Basically, this is exactly similar to this problem with a small twist, which you can figure out yourself. I would strongly encourage you to try to code this solution and get it accepted as well. Notice that getting a solution accepted is a very important part. Um, if you are facing difficulties in finding out the edge cases, I would encourage you to try that yourself. And if you are not able to do that still, feel free to paste your solution in the comment section below. I can help there. In the next video, we will be trying out how many LIS. This is a interesting problem. Basically, in this video, we have looked at what is the length of longest common subsequence, longest increasing subsequence. Now, this problem asks about how many longest increasing subsequence exist in the array. So, I would encourage you to try this problem by yourself. This is a slight modification of this problem that we've just discussed. And we will discuss this problem in much more depth in the next video. So with that, hope you like the video. If you like the video, give it a thumbs up and do subscribe if you haven't already so that you will get notified whenever I upload the next video. Until then, goodbye.